Welcome everyone. In this video lecture, we will think about a theory section where for a CMOS inverter propagation delay estimation using the concept of average current method. So before that, first we have to look for the CMOS inverter. So this one is basically a PMOS, that is our MP. MN is the NMOS. Both the gates are connected with an input say Vi, and we are taking a output to a capacitive load C. So here we can see that the Vi line, okay, the pink one is the Vi and the corresponding output voltage is the blue one. Okay, so when the input is 0, output is high, and when it is high, now after that the capacitor is fully charged, and then it start discharging. Okay, and then again it will go rise up. Okay, so this one is the simple concept. Now we have to think when the capacitor discharge. So when the capacitor discharge, okay, so the this time means when it is at high and when it is at half. So this point when is called the trans propagation delay from high to low. Okay, and this one propagation delay from low to high. Okay, so that thing we have to find tau PHL and tau PLH. Okay, and if we take the ideal one by keeping the both transistor mesh transistor both should be same. So we have to think about the tau PHL in this video. So how we have to evaluate the tau PHL? So now I am making a circuit when the capacitor will discharge. So at what time it will discharge? So for that one, that part I am just making a circuit. So when we are giving a high voltage, okay, VDD, when the input is high, okay, when the input is high, the capacitor is first fully charged. Okay, so I am just drawing the equivalent circuit. So during that time, the capacitor is fully charged. Okay, so V naught is VDD at point, this point, say t equals to say t1. Okay, at point t equals to t1, fully charged V naught. Then after it will discharge through this transistor. Okay, so for the time being I am saying some current will flow through the this NMOS transistor, that is our IMN. IMN be the current flowing through the NMOS transistor during discharge. So this one is nothing but simply we can say the equivalent circuit CKT I am writing during capacitor discharge. Capacitor discharge. Okay, and this one the input output waveform, no need to write, and this one is the CMOS inverter. So this one is the equivalent circuit when the capacitor discharge. Okay, so one more thing is very important. So if we draw how the current changes, okay, so initially when this one is maximum, I value, I mn will be maximum. Okay, after that when it start discharging, so this IMN value will going down. Okay, decreases. How? So that part we can easily identify by drawing the curve between the IMN. IMN. Suppose we have to draw the IV characteristics or in general we can say the drain current versus VDS curve. ID versus VDS curve. So this one is a IMN and this one we are saying the V naught because this one is our nothing but simply V naught. So it is somehow a simple most characteristics. Most characteristics. Okay. So in this case, what we observed that initially the current is maximum when it is VDD and after that it will go down to zero. Okay. So it so for the time being we can say for some point say P it have the maximum current I max. Okay, at this time the V naught value is VDD. Okay, V naught value is VDD, so we can say the current for this VDD is maximum here. Okay, and this one is saturated, so we can say that this point is in the saturation mode. Saturation mode. Then after what we observe that it start discharging and the current will also discharge. Okay, so current will discharge and if we are thinking about VDD by 2, so make it point some point say VDD by 2. So up to this point it will start discharging and at this point we can say this one is in the linear region and in between some point will be there, that is our VDD minus VT. Okay na, simple observation is there. So we are going from P to point say Q, P to point Q. Okay, so here it is in the maximum and it is in the saturation region. Okay, then after they start decreasing current IMN, it was the NMOS transistor start decreasing and reaches this point say Q, sorry, and at this point this value will be VDD by 2 and this one is VDD minus VT. Okay, so if we take this average current, okay, so this one is the point. So in this question, in this theory, if we think about the charge, so from point P to Q, so P to Q, so as we know the very simple traditional formula Q equals to CV, so the charge for point P to Q can be written as at this point it is maximum, that is our VDD minus VDD by 2. So it should be C VDD by 2. We have to equalize the charge. So this one is the equation number 1. Now next, one more important formula Q equals to I T. Now this Q, so during that time, how much sorry, how much time it will take from this point to this point, that is our tau PHL. So I value is nothing but simply we can say I am writing that I average into tau PHL. This one is very important. So equation number 2. I am highlighting we are using two concepts Q equals to CV and Q equals to IT. Then its value will be C VDD by 2. Okay, and this one is I average tau T PHL, high to low. Okay, now if we equate these two terms, equation 1 and 2, because the charge will be same. Okay, so if we equate Q equals to CV and Q equals to IT, what we can write CVDD by 2 equals to I average tau PHL. Okay, by equating 1 equals to 2. Okay, so from here we can easily say the tau PHL value will be C VDD by twice times I average. So I am saying this one is our equation 3. So now this one is a very important equation that we have observed for the tau PHL. Now in the headline I have written we have to find the propagation delay estimation using average current. So that average current we have to find. So this average current we can find as is very simple, but we have to practice. So this I average, C is known to us, VDD is known to us too. So the missing term is I average. So we can write as I average is nothing but simply half, half, and what is the current at that point? That is our I. We can write as I M N at point P plus I M N at point Q. I M N at point the drain current at point P, okay, through the NMOS transistor, drain current at point Q to the NMOS transistor, and the same thing, the same one can also be written as average. So that's why we are putting with 1 by 2. 1 by 2, or we can write as I M N P, which is in the at this point it is in the saturation region, in the saturation. So in bracket we can write it saturation plus I M N Q is in the linear region. Say this one is a equation number 4. So that one we have to find. So this one is very important. I average equals to half times of drain current equation to the NMOS transistor at point P and the drain current equation to the NMOS transistor at Q. At that time it is in the saturation at point P and it is linear at point Q. Now we have to find the drain current equation, very simple drain current equation. Okay, so I am calculating the value of I M N, we can write it P at saturation. So drain current in saturation. Okay. So ID, I am writing as saturation. We can write as Kn W by L VGS minus VT whole square. Sorry, by 2. Or better to write Kn dash. Kn dash W by L Kn dash W by L by 2 VGS minus VT whole square. Okay. And ID in linear region can be written as Kn dash W by L in bracket VGS minus VT into VDS minus VDS square by 2. VDS square by 2. Okay, this one is very important formula that we are going to use here. So I M and P at saturation is simply we can write as Kn dash Kn dash by 2 W by L. Okay. Now VGS is nothing but simply our get to source as a input. So input is our VDD. So we can write it VDD minus VT whole square. Why? Because VGS is nothing but simply our VI, and this VI is given as high value VDD when we are giving the input is high. Okay, so this one is one equation. Okay, no need to write more. Now one more equation for the at point Q when it is in the linear region. Okay, so in this case what we can write K and dash W by L. Okay, and this one is all for the NMOS W by L of N, and then after very carefully we have to write VGS, that is our VDD minus VT. You can write it VTN because this one for the NMOS, so better to write VTN, and then VDS. So VDS is nothing but simply our output voltage. Output voltage, at that output voltage, what should be the output voltage? VDD by 2. So we have to write VDD by 2 minus VDS square by 2. So we can write as 1 by 2 VDD by 2 whole square. Is it okay? Very simple calculation is there. Okay. Now we can break K and this W by L of N. We can write as VDD square by 2 minus VTN VDD by 2. Then this one is minus 1 by 4. So it should be 1 by 8 VDD square. Okay. This one clear. Up to this one it is very clear. Okay. So now what we can do, if we take 2 common, if we take 2 common, W by L of N into 1 by 2, it should be VDD square minus VTN VDD. We have to very careful in some situation for the solving this type of equation. So this should be VDD square by 4. Now again what we can write down, this one is VDD square and this one is minus VDD square. So one more line we can. Please follow a step by step procedure to solve this type of thing very carefully. 4 minus 1. So it should be 3 VDD square 4 minus 1. So 3 VDD square by 4 minus VTN VDD. Okay. So now we have to take the average. So we can put IMN. Say this one is equation number 5 and say this one is the equation number 1. Now if we put equation 5 and 6 in equation 4, so directly we can write I average equals to 1 by 2 times average. So we have to write 1 by 2. Now this one is K and S W by L of N by 2. Okay, this term I am writing VDD minus VTN whole square. Okay, so first term I have written. Now we have to write the second term. So again what we can write, plus K and S W by L of N by 2 we can write, then 3 VDD square by 4 minus VTN VDD. Okay, it is very simple, but you have to very careful when we are solving this type of equation. So now this term and this term will be constant. So one can write 1 by 2 and 1 by 2 and this, so it should be multiplied. So k and s w by l of n. Okay. Now we have to break this one. So it should be vdd square plus vtn square minus twice vdd vtn plus 3 vdd square by 4 minus vtn vdd. Okay, okay, this one. So now again, sorry. So this one will be 1 by 4 k n dash w by l of n. Then just solve vdd square plus 3 vdd square by 4. So it should be 437 vdd square by 4. 7 vdd square by 4 plus vtn square. Okay, this part is over. Then minus 2 vdd vtn minus, so it should be minus 3 vdd vtn. Okay, now one we can do one more thing. If we take vdd square common, so take vdd square common. Okay, so it can be written as 7 by 4 plus vtn by vdd whole square minus 3 vtn by vdd. Okay, so this one is I average stuff. Okay, take this as equation number 6 or 7. Okay, now what is our main equation for the tau phl? Tau phl c vdd by, I'm writing here, tau phl propagation delay from high to low is what? Once again, c vdd by 2 average, c vdd by 2 I average. Once again you can check. Okay, fine. So now everything is with us. So tau phl can be written as c vdd by twice 2. Then it should be 1 by 4. Okay, k and s w by l of n vdd square into next term, that is our 7 by 4 plus vtn by vdd whole square minus 3 vtn by vdd. Okay, so now this one and this one will be cancelled, vdd vdd 2 2 cancel. So once again I am writing tau phl can be written as 2c, okay, k and s w by l of n into vdd into 1 by 1 can write 7 by 4 plus vtn by vdd whole square minus 3 vtn by vdd. Okay, so this one is the expression for tau phl, and this tau phl expression can be written as c, one constant I am saying, alpha n divided by k and s w by l of n into vdd. Okay, alpha n c k and s w by l n into vdd, where alpha n, where the term alpha n, I am writing here. Alpha n is nothing but simply 2 by 7 by 4 plus Vtn by Vd square minus 3 times of Vtn by Vdd. So this one is very important. So that's why I am highlighting this one. Okay. This one is the expression for the tau PHL. Okay. For the propagation delay from high to low. Okay. And generally this alpha value, okay, this alpha value lie between 1 to 2. Okay. So this one is the expression. Now similarly, if we find the value of tau p, then low to high. Okay, for the PMOS it should be very similar. So we can write it alpha p by k and s w by l of p into vdd, and the term alpha p is very similar to that one, 7 by 4 plus vtp by VDD. So VTP take as a modulus because it should be, we have to take the positive. So minus 3 here we can also take VTP by VDD. So this one is the expression for tau PHL. Sorry, PLH. Okay, very similar expression we will observe. Okay, so this one is the expression, and now for the total propagation delay TP, we have to write as TPHL plus TPLH. So this one is also very important. Okay. So what are the thing that we have observed, that H we can easily identify that by equalizing or the matching the Kn Kp. If Kn equals to Kp equals to K, okay, and by keeping W by L of N and W by L of P equals to aspect ratio, same aspect ratio, then we can say tau P HL equals to tau P LH. Okay. So TP can be equalized by taking same channel, same aspect ratio for NMOS and PMOS with same transconductance parameter. Okay. TP can be minimized. This TP can be minimized by decreasing the value of C, because TP is proportional to C. So if we minimize the capacitance value, then TP will be automatically reduced. Okay, that thing we can also observe that. Also, if VDD increases, tau PHL will decreases, because this one is in denominator. Okay, so VDD increases, tau PHL decreases. Same for the LH also decreases when VDD increases. So these are the something, some concept that we have to take care. So this is all about this lecture. Okay, in which we have evaluated the tau PHL and tau PLH using the average current concept. So this one is the average current concept that I am highlighting. Means we have calculated the value for I average. Okay. In one case it is in the saturation region, and another case it is in the linear region, already highlighted. So this is all about this question. For more detail, you can also follow the book. It is our micro electronics book. Microelectronics by Sedra and Smith. Okay, so this is all about this video lecture. I hope you will enjoy this video. So thank you for watching this video.